In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwayne, and this is Soft Robotics Podcast. First, I would like to ask you how you would like to define who you are for the audience, maybe first time listening to you.
How to define who I am? Wow. Yeah, I think I define myself a lot through my work. So I would define myself as a roboticist for sure. I really enjoy working and puzzling on any kind of problem in terms of robotic manipulation and how we can make robots closer in ability to what humans can do, basically. Yeah, and that just is a lot of fun for me to think about.
Yeah, yeah. So I'm curious about your journey in robotics. I think you started with your PhD trying to solve the problem. Uh, for example, how to understand the scene for robotics and manipulation. If you can tell us more about the problem, what could be hard to challenge and still not solve it yet, through your work and generally as well.
Yeah. Um, yeah, so I started my PhD in 2007 at KDH in Stockholm. And I didn't know anything about grasping and manipulation at that point. I had been working on, I actually did what would now be an undergrad and master's in computer science. It was called slightly differently back then. Um, and I had worked on robots before, but I was doing more SLAM style approaches. So it was all about, SLAM with filters and using vision and all of these things. So when I came into my new lab at KDH and I met my advisor, it was the first time I even thought about grasping manipulation. And so I had a lot to learn. I read a lot of papers, so many papers. And then I did, as my first project, re-implement a new approach back then that was published in 2006 that was called Grasping of Novel Objects by Ashutosh Saxena and Andrew Ng, and there were also more authors in between. And they completely overthrew how people, I think, in majority at least, thought about grasping at that point. They just, they just, they had the idea of detecting grasping points in 2D images. And the way they did that is by training a model. In this case, it was a logistic regression model to take as input a bunch of filter responses with hand designed filters, and then do a classification problem out of this. So for every pixel, they basically checked is that pixel presenting itself as a good grasping point or not. And so they generated a lot of data in simulation, and then they also fine-tuned the whole approach a little bit on real data, and it was pretty amazing what you could do with a 2D grasp detector. And so I re-implemented that. I improved a little bit on this. And it was exciting because it was a completely new way of thinking about robotics and resolving also some of these strong assumptions that were made up till then. But it also had still a lot of limitations. It had no sense of geometry, in terms of 3D constraints. I talked a little bit about this. I revisited that entire project and the lessons I learned from this like about a year ago, and then I made like one of these talks about this. And so I personally, what I took away from re-implementing this approach was that one single point is actually not enough, but a parameterization of a graph that just tells you like, okay, here's the relative hand pose that the robot hand should be at when trying to grasp an object. That's a pretty good abstraction. And then maybe you have good controllers that actually execute the grasp. I also learned that we need to take closed loop feedback into account. So just open loop reaching and then grasping something, assuming everything is perfectly calibrated, just never works, which is something that wasn't obvious to me back in 2007 when I started. And I also learned that I would say the default approach to motion planning, which is avoiding contact by by all means, is not actually super useful in robotic manipulation, where you actually want to make very deliberate contact, sometimes not only with the object, but even with the environment around it. And so how to exploit that, this was really an open question that I kind of learned from this first project, that this is really important to look into.
Yeah, that's a great. Yeah, but I'm curious about what we could still be missing so far.
Oh,
You used to work in that, so what is missing really here?
what is still missing? A lot. I mean, we still don't have any robots at home that are useful, right? We have up till now, I think, robots that are useful in very constrained environments. And so what is still missing is the ability of robots to deal with any kind of unforeseen situation, right? So even if there is way more learning now in our solutions towards robotic manipulation, we still don't have good ways that can really capture concepts from the data an algorithm sees to generalize beyond the very simple scenarios we have trained a robot on, right? So I think there's still a lot of work, on generalization to be done, and this is in terms of generalization of the object, to the object that you're trying to grasp, generalization to the environment in which you're trying to grasp, generalization to the kind of tasks you want to do, generalization to the robotic hardware, to the sensors. All of these things are missing. And I think we made some progress for sure, but it's still surprising how little things really generalize.
Yeah, but I'm curious to ask you, which part do you think what you mentioned is most significant? Is it the design of, for example, for robotic hand, or the learning algorithms? Which one you can pinpoint is really maybe more significant here?
Yeah. I don't think I have I don't even want to, decide for one, because I think both of them are really important. And I actually watched your previous podcast with Ross to Drake, and I think you asked him a similar question, and what he mentioned was also that this one example from the PR2, or like the first version of the PR2 being teleoperated in this living room, and that robot, by being teleoperated, was able to do a lot, even though its hardware, the complexity of its hands and everything, was very, very low. Right? It had these parallel jaw grippers, and but yeah, so it was a demonstration of, even though hardware may be somewhat simple in the sense of it has not as many degrees of freedom as we have, for example, it can still do a lot once the right decision-making mechanism controls it, right? That was an interesting experiment, but I think it doesn't mean that we're done with developing newer and better hands, for example. I think it just shows us that people, or humans, are very good at learning very quickly how to deal with constrained situations. But I think if you make the hardware better, and we can talk about what that means, But if you make the hardware more capable or have more degrees of freedom that are somewhat easy to control, then or write controllers that are more autonomous, then I do think you can actually take the load off someone who either teleoperates this robot, or you can take the computational load of a decision-making mechanism that is maybe artificial.
Yeah. And do you think about the uncertainty here as well? Do you think that also relates? Because I think in soft robotics, we try to, for example, the hand design to adapt to different geometry. How do you see that approach when it comes to uncertain shapes and how you can adapt to that as well?
Yeah, I think I would say what, and I hope I'm not missing another approach, but I think we have done a lot of progress in picking and placing unknown objects, even from clutter, in the last year, certainly since I started my PhD. It's really quite amazing how that initial work that I had just described, that detected 2D grasping points in images, had really kicked off this learning-based approach and enabled a lot of progress and just picking up these objects that you don't need to know the complete shape of, right? And so I find that actually really impressive. So I'm thinking of works by Ken Goldberg's lab with Jeff Marlett, all these DEX networks, right? And that team did a lot of work, and they trained their models on actually simulated data to, then enable a robot to pick out good grasp. And there are still a lot of problems then to solve when it comes to clutter and how to maybe deal with failure or maybe learn from failure. But just this even open loop pick and place was really impressive. Also, the Google ARM farm was also interesting in that respect. And these are really systems that can deal with uncertain object shapes. They don't know what the shape of these objects is. Often they don't even know how these objects that are all lying on top of each other are segmented exactly, right? They just go for it. They have sometimes not even a concept of objectness. And so I think for pick and place, I'm sure to make it really robust and bring it to industry, there is a lot of work to do, to close these last percentage points, just like in autonomous driving, I guess, right? But I think that's the area of biggest progress. And now when it comes to more complex manipulation and you have uncertainty about object shape, for example, there, then things become much more brittle. So I'm thinking, I'm just going to take an example from my work that we did in 2020. I think we submitted a journal paper on this, and that one was about just this age-old problem of peg insertion, right, which appears in all sorts of contexts. But there we looked at how can we use feedback in the control loop, not just from vision, but also from touch, to basically perform successfully this peg insertion task. And in that context, we did investigate whether we can learn a representation of kind of this, whatever the robot perceives, either through vision or touch, that generalizes across variations of this task. And there we consider different shapes of the object, for example. And we really consider tight insertion tasks, so really low tolerance tasks that required quite some precision. And we could show that even with a representation that is learned on one object, this representation can be used also for solving the task with a similar object that has a different shape. But so that was pretty interesting, but it's still so far away from what humans can do in terms of generalization, right? So it's still interesting, like how much data we really need to make a robot do these kinds of things. But yeah, I mean, there's lots of work on this, but it's still always surprisingly limited what you can do in terms of generalization.
Great. But maybe I'm curious to ask you, since you mentioned human, what do you think maybe we need to understand more? For example, we speak about embodied intelligence. Should we You mentioned maybe better hardware, maybe better brain side. How do you see this concept in the design so that we can, match what we have as a human capabilities in manipulation and grasping? What kind of understanding more needed?
Hmm. Yeah. If I knew this, if I knew the answer to this, I think that would help a lot. But what I think one big question is really, or something that I always struggle with in my research work is what the right representations are that connect perception to control or planning of the robot arm. Because there are many different ways, and I'm always going. And my research work is really a mix and match of different options, depending on the project. And I wish there was like this fundamental abstraction or a fundamental way, or like some algorithm or a method that you can use to get a fundamentally important abstraction of the kind of sensory data you have that is useful for this task. But somehow maybe there is none. I'm not sure. So the kind of options that we're exploring, or that we're kind of bouncing back and forth in my lab as well, is to, for example, have a learned representation of all this perceptual data. It could be any modality at this point. And then use a maybe a learned policy using, for example, reinforcement learning that uses this learned representation as state feedback, right? So that's one of the ways that we represent data and connect between perception and action. And the other way is to, instead of relying on these learned policies that are often very simple and efficient, and especially in robotics, can be very difficult to learn on real data. I also like to use traditional controllers because they're actually quite well understood, but traditionally they assume a lot of ground truth knowledge about the geometry of the world, the geometry of all the objects, the geometry of the robot. They make assumptions about how contexts are formed and so on. And so, but still, lots of these concepts are, of course, extremely useful. And so and lots of my work, we also pick as a representation these interpretable quantities that these traditional controllers actually expect. And maybe the way we extract these quantities from raw sensory data is also through a learned method. But this representation is at least understandable, and you can maybe debug it easier and things like that. But yeah, each of these options has really its pros and cons, and so I haven't really found that there's this one solution. And I think that's where we still need to understand, to come back to your question, right? Like, need to understand a lot, like, what's the right interface between perception and action? Is there one that is useful? Maybe not. I think it's probably very task oriented, and then maybe also dependent on the whole context of the environment that you're looking at. So yeah, so for now it seems always a bit like hand designed what you really picked there.
Mm-hmm. But I want to ask you, in that process, is there a trade-off? Sometimes we have in design process a trade-off that we can't avoid. And what do you mention? Do you have any kind of trade-off so far? You can't really you can't avoid this trade-off.
I guess one of the trade-offs that we are basically sliding on all the time is this trade-off between bias and variance, right? So as I mentioned, like, we actually often know how to control a robot, right? But it assumes that you know all these things. So if you input the structure of the controller, but also of the representation, you gain a lot by biasing the whole system towards this. You need less data to potentially train components of it. You gain interpretability and easier ways to debug your system. But you may actually limit yourself in terms of the kinds of behaviors you may see. Right? So one of the things that so at the other end of the spectrum, right, you have a lot of variance potentially, right? So let's say you remove a lot of structure of things that maybe you think we actually already know. And like at the very end of the spectrum, right, like you have completely end-to-end learned system. Then what happens is that you need a lot of data to train the system, and there's a lot of variance if you're out of distribution, right, of what your system is actually going to do. And so you have not good ways other than collecting more data to somehow steer the system towards not, ending up in some catastrophic failure. But the kind of behaviors that you see by the system are things that you cannot necessarily easily design or model with traditional models, right? And so that's, I think, the really interesting part. So, I'm actually, as an example, I'm thinking about the OpenAI hand. I'm calling it the OpenAI hand, but I think the project was called Learning Dexterity, right? Where they had the shadow hand and it would rotate in hand all these different objects. And the kind of behavior that this hand showed, I thought was super interesting. I mean, something that would be very hard to model. And even if you could model it, the model would be so expensive to evaluate in runtime and like at test time, right? That it's not feasible to actually put it into a real-time system. And so that I thought was really cool to see on this hand. But then when you see how much infrastructure there was just for learning, for generating the data, how much data was needed to just rotate a cube, and then how much more data was needed to do the same with a cylinder, right? Then that's that was also somewhat a downer, I would say. And so, but again, like the behavior was really cool to look at. And so that is a trade-off, I think, that we cannot really avoid, or we haven't really found out. I think lots of people are basically working on this, including myself, right? Like how to ease that trade-off somehow, where to find the sweet spot, basically.
But I'm curious to ask you about maybe sometimes you have this counterintuitive behavior. I don't know if you have witnessed something doesn't make sense to you, and that's against models, or do you have any moment like that? And maybe
Yeah.
in life it was surprising.
Yeah, I think so. I guess all the time. Let me see for a good example. I guess so. Okay, so here's one thing that is maybe something that I, as a PhD student, didn't understand, or actually, it was when I transitioned from PhD student to postdoc when I realized a few things actually. But one was maybe something very basic, but I think a lot of people who are maybe focusing a lot on simulation would maybe find that also surprising. But what I didn't understand is that a robot may not exactly track a planned trajectory that you want it to go, but that it's actually doing something slightly different, and that this has a lot of influence on the success of your task. So during my PhD, I actually worked with an industrial arm that has sub-millimeter precision. It was a very stiff, very dangerous arm actually from KUKA. And then I came to the lab where I did my postdoc headed by Stefan Schaal. And they worked a lot with compliant arms that had mechanisms like cable-driven mechanisms, like the Barrett-Worm arm, or we worked with the lightweight KUKA arm that were all compliant and super nice arms. But what I didn't understand when I transitioned to these arms was that these arms are you cannot control them if you want to keep the compliance as precisely as this industrial arm, for example. And so this problem of how you deal with this uncertainty between perception and action, now exasperated, sorry, made worse by this arm that is not as precise, became even more urgent or more important, actually. Yeah, so I think this was not super obvious for me at that point. And actually surprising. And the other thing that was surprising was, again, like when I came out of my PhD, I had mostly worked with the idea that you need to avoid the environment as much as possible, except from these 2 points maybe on the object, on these few points on the object that you want to grasp with your hand. But you have to carefully, thread the arm through all these potential clutter. And to be able to do that, you need to understand the environment and reconstruct it as accurately as possible. And so when I joined this lab as a postdoc, they had not done manipulation before I came. They basically jumped into a DARPA challenge. And so they had to kind of come up with solutions towards solving these problems that were posed there, like picking up objects from a table. And so because they were controlling their arms in a compliant way, there was no danger in actually getting in touch with the environment or with the table, for example, of touching it, of sliding along it, of maybe caging things by sliding on them. So all of this was suddenly possible. And so their solution to these things were actually very robust because they had this compliantly controlled arm to exploit the environment and make grasp thereby more robust. So that was one ingredient of their solution. And it was completely different from how I had thought about this before. And it was surprising and really eye-opening as well. Yeah.
Do you think it's so necessary for you to, since you mentioned the model sometimes when it comes to compliant arm, do you think it's necessary to, I don't know, how do you see simulation so far? Because it's still, there's a gap here, but from your experience, to which level do you think we can, make simulations so realistic and we don't have to have the expensive data? Do you think that's solution or doesn't make sense to you?
That's generally definitely not the case. But there are some cases, I think, where things are already easier in terms of tasks, right? And then, when it comes to soft robotics, what this podcast is about, right, and what you're working on, I mean, things are terrible, I think, in terms of simulation. I'm just starting on working much more in depth, also together with my postdoc, Rika, on manipulation of deformable objects. And yeah, simulation environments are so terrible. I mean, they're brittle, they explode all the time. I mean, I don't know what your experience is actually, but that's kind of my experience. And also, they're slow, of course, as well, right? Like they're brittle, they're inaccurate, they're slow. So I don't think they're great for testing your idea, right? Like, because you can't like possibly test everything in the real world, right? But sometimes probably for deformable objects, sometimes it might be actually easier to test things in the real world. But I think in general, simulations are very good as sanity checkers, right? If in this enclosed world, does your idea, your algorithm, your controller, your perception mechanism, whatever, does it actually work? But I think when it comes to deformable objects or soft robots or things like that, soft sensors, all of this, porting this directly from simulation to the real world, at least at the moment, it's definitely not possible or very hard to do, or in very limited setups, I would say. I don't know. Do you agree with that, or?
Yes, I have experience also. I think in non-linear material, for example, it's very hard to simulate sometimes. And yes, I share with you the same vision. So there's a lot to be done. And I think Russ was speaking about that in Drake tool. But yeah, I'm not sure how it will turn out. But you're absolutely, mentioned the same struggle we have.
Yeah, I would say actually I'm learning that there are a lot of different simulators out there that have some version of deformable objects implemented in them, but all of them have a problem somehow in the ways I just described, right? Accuracy, speed, um, and just brittleness, general explosion of things. So so I would say we're far in that area from porting to real. And then when we come to rigid objects or grasping, I think some tasks I would say are easier to go from sim to real. And it depends a lot on, again, on the abstraction that you're using. That's at least my experience. So for example, I can give you one example where we had a project where we looked at different action spaces for reinforcement learning algorithms. So if you have a policy that takes in a state, it outputs an action A. And that action A, when you try to control a robot, could be many different things, right? It could be the torque at the joints, it could be the velocities of the joint, it could be the positions of the joints, it could be the end effector position, and so on and so forth, right? It could be anything. And it turns out that action space that you use has a lot of influence on how easy or hard it is to learn certain tasks, and also how easy and hard it is to transfer from sim to real or from one robot to the other robot. So in this particular study, what we found is that when you have a contact-rich task, then actually using as output of a policy the end effector displacement and the impedance gains of like how much it's basically force applying to it, it makes learning these tasks much easier. And we could actually show that we can take the same policy, transfer it to a different robot that has a different kinematics, has completely different kinematics, and we could also port it to a real robot actually with the same kinematics. And that didn't, of course, work with if you send joint space commands, right? So I think again, like this abstractions for the state, but also for the actions that you're sending, actually make a huge difference when it comes to sim to real transfer as well.
Mm-hmm. Great. So since we closed the entire few question, maybe the first one about, do you think that designing robots should be more predictive? For example, from your work, should be more predictive and less depending on the feedback? More, I think that's something also speaking about robotics, to be more predictive, the behavior, and you shouldn't really rely so much on the feedback.
Okay. So that's a good question. This is like another trade-off that we that we're always dancing on, right? Like and jumping like back and forth in a way. So again, like in my work, we have done both having feedback policies or feedback controllers that take in feedback in at every possible cycle at every time in the control cycle, and then immediately react to it. But we also played around with policies that are actually open loop executing for even a few seconds or maybe 200 milliseconds or something, a particular plan or a particular trajectory. And maybe this has been learned, right? But it would be an open loop trajectory that this robot follows. And and so that choice, when I look at these particular works that I'm thinking about right now and from the lab, that choice was made for easier learning, because if you're trying to learn a feedback policy, you typically just need way more data than learning a policy that maybe generates an entire trajectory that stretches over a certain amount of time and does like one motion. But of course, when you open loop execute these trajectories, there will be deviations from what you've seen during training, right? So we definitely also seen that some feedback to adjust this initial trajectory would be very, very useful, right? But I also do think that learning, and this has been shown by others as well, that learning some corrections rather than the feedback policy from scratch, for example, is much easier than learning an entire feedback. It's much easier than learning an entire feedback policy. So that's one of the answers I have with respect to your question. And then the other one is the other thing I'm thinking about is that I think when a robot or even us, when we learn a new skill, then I think we do rely on a lot of feedback. And at some point, often these kinds of skills may become automatic and open loop, actually. And so that feedback is not necessary anymore at that level of detail, right? And so maybe you only react if something really wildly different happens during executing this particular motion. So I don't know how to do that, but maybe what would be interesting is to, when you are sufficiently skilled in a certain task, you can go from a policy that relies, or controller that relies a lot on feedback, on more open loop execution of these things. This probably shouldn't be encoded in the design, right? Because then you don't have that stage where you are learning new things because you still need all these sensors, and at some point you can maybe abstract away from that. But I don't know if you should leave out sensing right from the beginning, right, in a robot.
I think two questions left. First one, how do you deal with doubt when you have new ideas? Or maybe, how you deal with doubt or...
Oh, yeah. Yeah. I mean, you never know if an idea works, right? Never. Unless it's, like something written in a textbook. Even then there's a chance that it was wrong. But so how do I deal with this? I guess, and that's maybe easier for me because I made a lot of experience with failure, but I'm thinking that when you have an idea, you should always remember that it might not work. And I definitely, when I started my PhD, I did not keep that in mind, that might not work as well as I think, that idea. And so it was very frustrating when it didn't work out. But now, after all these years, I'm kind of have this experience like, okay, I have this idea, but as usual, it's not going to work as well as I think. But if we don't try it, we will never find out, and we will not learn anything from it if we don't try it. And so, of course, you cannot try all the ideas. You still have to kind of vet them for a while, right? And discuss them, hopefully, with people. But I think it's just important to keep in mind that ideas may not pan out at all. There might be counterintuitive things happening that or you've forgotten about something, right? That only you remember once you implemented it, and things don't work out, and then you remember, oh yeah, that's because of that. So how do you deal with doubt? I think, moving forward and trying things. And so I found a really great deck of slides from one of my colleagues at Stanford. He's actually not in robotics. He's called Michael Bernstein, and he has a lecture for undergrads who want to do research. And so it's like a seminar on doing research for undergrads. And one of the lessons is called Velocity. And there he talks about that every research project has a swamp, a phase where you're stuck. where you're just wading through stuff. You have no idea what's going on, why things are going wrong. And this lecture is about how you get out of it as fast as possible. And so one of the things he has in the slides is that you have to be able to try different hypotheses as fast as possible, right? And so it's always, for some ideas it works easier than others, but you should always think about the most minimal, tiniest example to test, that you can test as fast as possible, to see if there's a path, if your idea has even the chance to work, or if you're stuck because of a certain hypothesis, right? And so that approach of thinking about a toy example, a minimal example to test your hypothesis, I think that allows you to have velocity. And if you have any doubt, you can confront it in that way, right? Like, okay, I have this doubt. Why is that? Okay, how can I test this, right? And I think that's at least, what I'm also trying to recommend to my students, and sometimes easier than in other times to do. But yeah, I think that's one way.
That's excellent. Thanks for sharing that. That's very inspiring. And two questions left. The first one, I think, what could be the most important quality? You mentioned failure, and yeah, it's a lot of pain sometimes through the journey. But what could be the most important quality for you?
I still have to enjoy that work, right? So I think there are definitely sometimes frustrating periods in research, right? When things don't work out, or your paper or your proposal gets rejected all the time for me. So it's very frustrating, and it keeps being frustrating. But as long as you still enjoy maybe most of the work, if you look back, if you can look at your achievements and see joy in them, or you explore a research idea and you see joy in them, if this is something I think is most important for me to keep going, right? Like that I still have this curiosity and the interest in robotics and in these different problems. And and this is something that keeps me going, right? Like even through maybe some more difficult or frustrating experiences that definitely happen as well, right? And so that's that's something I don't want to miss as a researcher.
And I don't know if you have any advice you received maybe through a career or life, and was a life changing, and stick to your mind. Yeah.
That's a good question. It's really funny because I did like an Ask Me Anything series in my department with all my colleagues. And this is one of the questions I'm also asking. And then people, and now I'm here, I'm getting these questions, and I'm like struggling finding a good answer. I certainly had a lot of great mentors throughout my career. So there were a lot of people who gave me good advice, including my PhD advisor uh, and my postdoc advisor, and also my advisors. Okay, here's one. Here's one that is a good one. Say no more often. So, like there are lots of people who are asking you to do lots of things. And, especially if you are from any kind of minority, if you're a woman or a minority, right, you have this additional bag of questions that is being carried towards you, right, to do this or that for diversity, right? Like it often happens, and you're expected to do it kind of as a service to the community. And so and of course there are other things that you're being asked to service, like not just on diversity but on other things, and it's okay to sometimes say no, right? Because you can't possibly do often all of these things that are being asked from you. And so that's, I think, one advice I have gotten from some great mentors, and I think that is also good to hear from others, for others as well. Yeah.
I agree with you. Thanks for sharing that one. I don't know if you have any final words for robotics community you would like to say before closing. Any final words?
Final words. I really like the robotics community, I have to say. I'm comparing it sometimes with other research community, and I have to say that I actually remember one researcher who was not from the robotics community, but who I met at a seminar, who said like, "Oh, the roboticists, they are always so nice to each other because they know how much work it is to make an actual robot work and how hard it actually is, and so they are mostly very nice to each other when asking questions. While in other communities, it can become quite competitive, and so." Yeah, I guess my final words to the community would be stay like this, stay nice to each other, and be welcoming and inclusive as you are. And I think there's also still a lot to improve, but I think we're starting from a good base.
Thanks so much, Jeannette. Such honor having you on the podcast, and I really enjoyed it. Thanks a lot. Thank you.
Thank you, Mara, for inviting me. It was really fun.